All right, we're still in chapter 1 on ingredients of change, functions and limits, and this is section 1.4. We're looking at linear functions and models. So linear functions can be used to model situations in the real world. It's the simplest function used to describe change. And we have to kind of remember the slope-intercept form of the line is y equals mx plus b. So that's going to be a key one. You also might need to remember the y minus y1 equals m times x minus x1. If you have a point and a slope and you need to come up with the y equals mx plus b, then you have to simplify this and then get it back into that form. So there's going to be times we're going to use both of them, but y equals mx plus b is our standard form. Now for a linear model, algebraically, it's f of x equals ax plus b. So instead of y, we're using f of x. Instead of m, we're using a, and then we still use b. So where a here is the slope, b is equal to what f of 0 is. Basically, we plug in 0, and what comes out is we just get b, and that's the y-intercept. And both of these are constants, okay? Now verbally, a linear model has a constant rate of change. And so if you think about a linear model, it's going to go up here and it's just going to constantly go up 2 over 2, up 2 over 2, up 2, very, very boring. Or we can go right 2, down 2, right 2, down 2, depending on if you have a positive or a negative slope. Now graphically, the graph of a linear function is a line with the constant a being the rate of change of the function, where you have a being either a slope of positive value or a is negative and you have a negative slope. Now the constant b is the output when the input is 0, and it's known as y-intercept. So when you have x equals 0, then you get your b wherever it crosses the line on the y-axis. And so here you have b as negative, here your b is positive, okay? So let's look at an example here. It says, give the slope of the line defined by the equation, write the rate of change of the function in a sentence of interpretation, and then evaluate and give a sentence of an interpretation for f of 0. All right, well, let's look here for the first one. So the first one, if we look at that, we have f of x is equal to 1700 minus 20x, okay? And this is for under overcrowding conditions on an assembly line. The productivity is equal to this function. And that's in units where labor is x workers over capacity. Okay, so what we're saying here is this is our equation. In an ideal world, we're going to produce 1,700 of them. But if we're working in overcrowded conditions, we're going to be minus 20 times x from that peak of 1,700, okay? So that kind of really comes into play as far as how that's going to be working here. So if we think about what is the slope, well, the slope, well, in this case, we're calling slope A, and that's equal to a negative 20, okay? And so that would be what they're asking for in that first part. And so next is they're asking, write the rate of change of the function in a sentence of interpretation. All right, so what do we have here? So if we think about this, we're having units of when labor is X workers over capacity. So it's units over capacity. All right, so how do we want to write this? I'll put a measure as units per basically worker. Capacity per worker is what it's looking for. Okay. And so that's going to be our rate of change. And so the more the number of units we make is going to be defined by how many workers we have. So the more workers we have, the smaller units we're actually going to make at a certain point, because 1,700 is our max, and we're going to subtract off that units per worker based on minus 20, then units per worker. And so now we want to evaluate and give a sentence interpretation of what f of 0 is. Well, f of 0 is going to be basically when there's no overcrowding, okay? So there's no excess workers to make the unit start going down. So f of 0 is no excess workers. And if you plug in 0 for x, that's going to be equal to, like we've been talking about, 1,700. Okay. So that means 1,700 units produced. That's what it's really talking about. And then every time we have one worker extra, we're going to subtract off 20. So if we have one, that's going to be 1680 units produced. If we have two workers too many, then that's going to be minus 40, so it's going to be 1660, and so on. Okay. All right, so the next one says the number of people of age X years in a certain country is f of x equals negative 0.5x plus 3.2 million people. Well, what does that tell us here? All right, well, that tells us that we have a slope of what? Well, our slope is going to be our a, which is tied to what the x is. So here a is equal to a negative 0.5, okay? Now, what does the rate of change of the function in a sentence of interpretation, what's the units for that? Well, we're going to have million people, it looks like, per year. So it's going to be million people per year. Okay, so the output is million people, input's going to be the year. And so because we have X years and we have the number of people is going to be the output. And so what are we basically looking at? The number of people is basically decreasing by 0.5 million per year. Okay, so there's probably that many people dying per year is what it's going to be. Now, what does f of 0 mean? F of 0, well, that's equal to 3.2 million people, because if we plug in 0 here, that goes to nothing. We have 3.2 million people. And if that means we're adding that many people per year, well, what does that indicate? Well, that means we're going to have 3.2 million people per year born. Okay. And so there's going to be that many babies per year that are doing, and we're going to lose 0.5 million people per year who actually die. All right, so now we're supposed to write a linear model for the given rate of change and initial output value. So the cost to produce plastic toys increases by 30 cents per toy produced. The fixed cost is $50. All right, so if we're raising the price by 30 cents per toy and the fixed cost is $50, those aren't the same units. And so since dollars is the bigger units, what I'm going to say, well, this is going to be 0.3 dollars, okay, per toy. So I'm going to convert it kind of to the units, so we have the fixed cost and the toys are going to be the same. And when we do that, what does that give us? Well, a fixed cost, usually cost is C of X is equal to, and it increases by 30 cents, so it's going to be 0.3 times X, so however many toys we produce, plus a fixed cost of $50. So $50 is going to be there no matter what. And if we don't produce anything, and that's 0, we're still going to have that fixed cost of $50. But, you know, if we produce 100 toys, then we'll have 100 times that, so that'll be 30. So that'll be $80 for the total cost when you produce that 100 toys. All right, so now we're going to do fabric. Fabric sheeting is manufactured on a loom at 4.75 square feet per minute. The first 6 square feet of fabric is unusable. So basically we're just scratching that first 6 feet, so we don't have to worry about that. So our rate, if we think about this, and we didn't really do that, that's our rate, and that was our fixed cost. And so our fixed cost is usually our B, and this is our A. And so here, the loom is 4.75 square feet per minute. So that's a rate. And so that would be our A. Now the first 6 feet of fabric is unusable, so we have to delete that part. And so we're going to say, well, that's going to be a -6 because that's just going to not be usable. So -6 feet squared. And so we want to write some kind of function with this. Well, fabric sheeting is manufactured, I don't know, so maybe fabric of X is equal to, well, we're going to take 4.75 times some X, and then we're going to subtract off our 6 because we can't use that first 6 square feet. And so that would be an equation or a linear model for the rate of change, which was, you know, that's how much is manufactured on a loom per minute. square feet. And we have to get rid of those first 6 square feet. And so that would be our function after that. All right, so we kind of talked about the linear model y equals mx plus b, and the other one y minus y1 equals m times x minus x1. But now we need to figure out, well, how do we get a slope? Because if we think about it, those equations both assumed we had the slope. But what if we're given 2 points? Well, then we have to understand how to find that slope. And to find that slope, what we're going to do is our slope is equal to f of x1 minus f of x2 over x1 minus x2. Well, what is f of x1 really? Well, f of x1 is really just y1. So if we think about that, that's the output after we plug in x is 1. And so what is the output after we plug x1 in? Well, that's just y1. So what we can say is this is x1, this is y1. And then f of x2, what is that really? Well, f of x2 is really just y2 because that's the output after we plug in x2, and the output after x2 is really y2. And so we can say this is x2 comma y2, okay? So with that in mind, what we have is we can find the slope, and then it wants us to write that linear model for these 2 points, which means we're going to have to use that point slope form. And so let's first find our slope. So slope is m usually. In our book now they're using a. So if you feel like you have to use m, that's fine. I'll probably switch back and forth depending on if I remember to use the a or not. And so we're going to use basically our y1, which we're going to say is 6, minus the f of x2, which is y2, which is 9, over, and now we have x1, which is 4, minus x2, which is -3. And so 6 minus 9 is -3. 4 plus 3 is 7. And so that would be what our slope is. Now, what does that equal on actual numbers? Well, let's see. 3 divided by 7 is 0.4285714,286. This looks a lot nicer, I think. So we'll just use the fraction form. And now we're going to use the equation y minus y1, and y1 we said was 6, equals m, which is -3/7 times x minus x1, which is 4. All right. So now what we have to do is we have to distribute here and then add to the other side. So we have y minus 6 equals -3 over 7x, and then that's going to be plus, that's going to be 12 over 7. Now we'll add 6, and we have to get a common denominator. And so y equals -3 over 7x. And now we have a 42/7 plus a 12/7. So that's going to be 54/7. Okay. Now that would be an exact model. Now what is the actual other way? We could do it. We could round it to decimal places. We could say, okay, well let's take that 3 divided by 7, and we could say, okay, well this is going to be y equals the -4. Oh, actually, I need the 0.4 first. -0.4, and that was 2, 8. I don't know, maybe we go 4 decimal places, 6x plus, and then 54 divided by 7 is equal to then 7.7143. And so, decimal form with rounded answers versus the exact form with actual fractions. So both ways are a linear model. This one will be more exact because there will be no rounding, and a lot of times when you round, even if to the 4th decimal place, you're going to have slightly different answers than if you didn't round. So sometimes it's better to leave it in the fraction form and then do all the division. Take -3 divided by 7 times whatever your x is plus 54 divided by 7 equals, and then whatever that y is, you can round at that point. And so that would be kind of something ideal, or you can keep it as a fraction if it makes it a nice fraction. All right, so I'm gonna pause there and then come back with another part later.